Hello everyone, in this video we are going to introduce the higher rule, which is the rules that we will apply to quantitative analyze the strengths of acid and bases. So what does HIRE stand for? We start from E, so this is the most prioritized, going this way, most prioritized. E stands for the elements, and R is resonance. I stand for induction, and H stand for the hybridization. So where can we apply the higher rules? So higher rule is the rules that we will use to qualitative analyze the strength of the acid. But how? So if we have one acid, okay, acid work as acid, basically it will donate proton and then form its conjugate base. So imagine if this conjugate base is stable. That means this reaction favors to go to this place because the conjugate base is more stable. At the same time, that means this acid will release or donate more proton. That give you a better acid. So the general rule here is if the conjugate base is more stable, the parent acid is stronger. So basically, when we apply the higher rule, what we are looking at here is not the acid. What we are looking at here is the stability of the conjugate base. More stable, that means the parent acid is stronger. So the next question is, how do we know if this conjugate base is more stable or less stable? That is where we will apply the higher rule. So let's begin. First, the most prioritized thing you want to look at is so-called element effect. What does that mean? Let me give you one example. If we have the hydrogen, which is connected to oxygen, compared to this hydrogen on this carbon. So this is carbon. I'm going to highlight this hydrogen. You will be able to see that there's 3 hydrogens. We are only looking at one of it. Okay, one of it. So which one is more acidic? We don't know at this moment if we do not know the pKa value. So we are going to look at the quality of this acid. But instead of looking at quality of this acid, what we are going to look at is when it is donating that proton. What is the conjugate base, the stability of the conjugate base, the quality of that conjugate base. So imagine if some base grabs this proton. So what we will end up with, this conjugate base will be this one. Compared to the second case, when the hydrogen is on the carbon, if you lose one of the proton, what you will have here is this carbon now carry that lone pair with a negative charge. So in this case, both conjugate base end up with one positive charge with that lone pair. So which lone pair will be more stabilized? That means that base will be more stable. And then the parent acid will be more acidic. So in this case, what we have here is lone pair on oxygen and a lone pair on carbon. Oxygen is more electronegative. That means it can stabilize the negative charge better. So that gives you a more stable base. That gives you a more acidic parent acid. So this one will be more acidic based on the quality of the conjugated base is more stable based on the element effect. Also, if we have a more stable base, that means this base like that negative charge, like that electron pair, which means that this base do not want to share that electron pair. That means that base is a weaker base. So this is based on stability of the lone pair that is formed here. And if we are looking at the element effect, if this proton is bound to a more electronegative item such as oxygen, nitrogen, or fluorine, that hydrogen will be more acidic compared to the other hydrogens on carbons, for example. So that is element effect. So what if the element effect type, meaning that this hydrogen we are looking at is on the same type of element? So the next we are going to move on to the resonance effect, the R, resonance. So for example, if we start with, again, we are going to use ethanol, and then the next one what we will have is, let's just do this one, acetic acid. So compared to ethanol to acetic acid, if we do not know the pKa, which you should know at this point, which one is more acidic? Again, we are looking at the stability of the conjugate base. Let's get this proton get lost. So if you deprotonate the ethanol, what you will have is this S oxide. And if you deprotonate this proton, what you will have here is this negative charge is on this oxygen as well. So based on what we just talked about, element effect, they are tied, both negative charge formed on the oxygen. However, on the second case, this oxygen lone pairs is allylic position. That means it can be stabilized through the resonance. What does that mean? We can draw out this resonance of this conjugate base. That shows us the negative charge can be spread out through the resonance. How to spread out? The negative form will not just sit on this oxygen. It's spread out through the resonance, through this pi system, through this oxygen and this oxygen. They kind of share this negative charge. So what does that mean? That means it spreads this negative charge through a bigger space that gives you a more stable negative charge. So in this case, this negative charge stabilized by resonance, meaning it's more stable. That means this acetic acid is more acidic compared to the ethanol on the first case. So that is resonance effect. So in this case, when you form the conjugated base, if it's allylic lone pair, then you need to think about resonance effect. So that is the second effect after the elements. So the third one, higher rule, the third one is I, that is induction. So I is induction. So this in fact is induced. Induced by what? Induced by the electronegative items. Okay, what does that mean? Let's look at if we have, first we have acetic acid, and then the next what we are going to have is we are going to add one of fluorine on this carbon. And then the next one we are going to have a fluorine that move out one more carbon. Okay, so in order to look at the stability of the conjugate base, first step, okay, use higher rule. First step is deprotonate. So we'll deprotonate that this oxygen will carry that negative charge now. And the same for the second one and third one. So now what we have here is all the negative charge formed after deprotonation is on oxygen, so element rule tie. And second, they are all allylic lone pairs, and it can resonate onto the top oxygen, so they are all tie. The difference here is, if we are looking at the second one, we have a fluorine which is electronegative and is 3 bonds away to the negative charge that formed. So 1 bond, 2 bonds, 3 bonds away. So what it does is, because it's electronegative, it cannot draw the electron density towards itself through the space. And so does the third one. However, the third one, fluorine, is 4 bonds away, 1 bond, 2 bonds, 3 bonds, 4 bonds away. So it still can induce that attraction to draw the electron toward itself. But because the distance, it will draw the electron toward itself a little weaker compared to the second one. So in this case, because the induction comes from the electronegative items, the second conjugate base is the most stable one, and followed by, this is the first one, followed by this one, and the third one. So based on the stability of the conjugate base, what we have here is the most acidic acid in this case, and then this is second one, and this is the least acidic acid in this group, based on the induction effect. So the last effect is, start with H, is hybridization. So what does that mean? So remember that if you have sp3 orbital, if the lone pair sitting in the sp3 orbital is 25% s character and 75% of p character. What does that mean? S orbital is a sphere, is close to the nuclei, which is positive charged. And if you are looking at the p orbital, I'm just arbitrarily draw one p orbital. It's kind of low, so it's kind of away from the nuclei, which is positive charge. If you move down to sp2, then sp2 will have 33% of s character and 67% of p character. If you go down to sp, you have 50% of s character, 50% of p character. So what does that mean? If you are looking at the size or the shape of the sp3, sp2, or sp orbital, in terms of the distance to the nuclei, which is positive charge, sp probably a little further down if you have electron pair sitting there compared to the problem sp2, and of course sp, you will be more these lone pairs will be closer to the positive charge nuclei. So how that will help us to determine stability of the base, conjugate base, and the acidity of the acid. For example, if we are looking at this hydrogen on alkyne, I'm just going to draw out this hydrogen. You don't need to, but I just want to show you. And compared to this hydrogen right here, you will have two. We will only deprotonate one. Or this hydrogen, okay, this hydrogen, you will have 3 on this carbon. Okay. So imagine if you deprotonate this hydrogen on alkyne, this lone pair will sit on a sp carbon. And if you deprotonate alkene, this lone pair will sit onto a sp2 carbon. If you deprotonate one of the proton on ethane, is alkane. That lone pair will sit on sp3 carbon. So this is sp3 carbon, this is sp2 carbon, and this is sp carbon. So for sp carbon, it's closer to the lone pair, to the nuclear positive charge. sp2 lone pair, little further, and sp3 lone pair is even further. When the negative charge is further away from nuclear positive charge, that means the attraction is less. So the lone pair in the sp orbitals will be the most stable one because it's the closest to the nuclei, and this will be more stable, and the least stable one is the lone pair in the sp3 orbital. So because the first one is the most stable, so the first alkyne will be the most acidic, followed by the second one, and this is the least acidic protons. So that is the hybridization effect. So if the other element effect tie, resonance tie, induction tie, then we are going to look at the hybridization. So this is how we apply Higher rule to determine the acidity of the protons on the molecule.